Okay, so in the last class we discussed about what happened during the 1897 earthquake in Assam, various cases of liquefaction that occurred in Assam, in Bihar as well in 1934, before Kasakandre 1936 defined the that what liquefaction actually means. So before that itself, there was cases of liquefaction in northeast India as well as various parts of India. Then we discussed about the earliest criterion as given by Arthur Casagrande in 1936, based on the critical void ratio line, and if a soil is in a state of void ratio above the critical state, critical void ratio line, then that soil has a contractive behavior when shear stress is applied, and that soil, when shear stress is applied in undrained case, positive pore pressure will develop, leading to reduction in the effective stresses, and ultimately the soil will liquefy. And then we saw that that criterion only cannot explain the various factors which are governing the way soil behaves during liquefaction. So to study that in detail, we take help of laboratory studies, obviously the triaxial test, which is as we have seen in our classes where we have discussed about the triaxial tests, what are the advantages, various advantages of the triaxial test. So in uh, liquefaction study, so mainly we have the three types of triaxial test. One is UU, one is CU, and one is CD. And we observed that especially the consolidated and undrained shearing is particularly applied for studies of soil liquefaction, or for the soil liquefaction study. This particular test is mostly applied. So how the pore pressure develops and how it leads to reduction in effective stress, this particular stress type of triaxial test is most efficient in simulating the various condition. So we started with the triaxial test. So here in case of triaxial test, what we have is we can apply the cell pressure. So we can build up the water pressure here. All right, water pressure here, and that water pressure is transmitted through to each and every point in the water, and that water in the cell, whatever pressure is developed, it transmits to the soil through the rubber membrane. All right, through the rubber membrane. So only the stresses is acting on the soil, and the water cannot penetrate from the cell into the soil. Obviously there are drainage paths where we have, if we want to allow drainage from and into the sample, so we have drainage paths, and we measure the pore water pressure. What is inside the soil sample. So before doing the cyclic triaxial test, we need to understand how the stress condition is to be applied. Right? We need to study the stress condition which is applied, which is occurring in the field. So in the triaxial test, only thing we can do is we can apply the cell pressure. And we can apply the deviator stress. So it will, at one cycle it will increase, then in the other cycle it will again decrease to this value. All right, then again in the other cycle it will again increase, and then again decrease. So that is a cycle of loading. Now how to replicate the in situ condition, right? So in the in situ condition, so Seed and Lee in 1966, so Seed and Lee in 1966, they proposed that the major part of soil deformation in most of the earthquakes may be attributed to the upward propagation of shear waves. all right. So it is attributed to the upward propagation of shear wave. So in the rock, so this is a rock, so the earthquake motion is applied to the rock. So the rock moves in this direction once, then in another, in the other cycle it moves in this direction, all right. So it undergoes shear motion, all right. So that wave, when the rock moves in this way, so the soil tends to move in that way, and then again when the rock tends to move in this way, it tends to pull the soil in the other way. So there is a shear wave generated, all right. So if a particle is here, so once it moves in this way, once it moves in this way, similarly there is a particle, so that it will move in this way and that way, first in this way, all right. So this is the shear condition in the first cycle. In the second part of the cycle, it will move in the other way, all right. So mainly the shear in the sample or in the element, the shear stress in the element is changing, all right. So if I now consider the steady state, so this soil has sigma v and sigma h. So there is a vertical stress and there is a horizontal stress, and then we can plot the Mohr circle of the stress condition of this element. So this is the stress condition. So this is sigma h, all right, and this is sigma v. Obviously sigma v will be more in at rest condition, all right. So we can say it is k naught. So k naught we know it is mu by 1 minus mu, all right, then 1 minus sine of phi dash, all right. So various values of k naught is there. So we know we have the k naught, so ultimately sigma v is more than sigma h. So we can draw the Mohr cycle at that condition, and we have a mean effect, this mean confining stress, all right, or a constant mean stress. Now when earthquake shaking or earthquake vibration is applied, so the soil mass tends to move in a shearing pattern, right, and only the shear stresses changes. So only shear stress will change, all right, and the mean will remain constant. That is what Seed and Lee 1966 they proposed in the in situ condition. So what will happen is that, so the mean will remain constant and there will be an increase in the diameter of the Mohr circle, all right, and again it will increase. So this is the maximum state, and it then start to decrease, all right. So this is a cycle basically. So this is a cycle. So in this pattern it will increase and decrease in situ condition, all right. So the mean being here. So once it will increase and then again it will decrease. Again in this pattern it will go on, all right. So that is the stress condition during earthquake loading in a soil element in situ. So the soil will be sheared first in this way, right, and then in the other way. So sigma v and sigma h remaining constant, or the mean remaining at the same point. So that is why it is called constant mean, and only the shear stresses will increase, then come down, go the other way, all right. So this is the other way, again it will come down, all right. When it will come down, the this Mohr circle will collapse, all right, it will come down again. Similarly again when it will go up, the Mohr circle will expand, all right. So this cycle of increasing and decreasing diameter of the Mohr circle will go on at the same point, at the same mean constant point. So this condition is called, this condition of loading is called the constant mean extreme principal stress condition, and it was advocated by Seed and Lee in 1966. So we have this condition preserved. All right, so the condition of the in situ stresses being preserved, we have the earthquake loading, which is only applying shear stresses in cycle. All right, so the diameter of the Mohr circle will increase and decrease and go the other way, and again decrease and again go the other way. All right, so this cycle will continue. So this is the initial state. From the initial state it will increase and again decrease. All right, so that is the loading condition. Now in the laboratory we have the cyclic triaxial test. Now we have to replicate that condition. Now thing is that in the laboratory only thing we can do is we can apply the cell pressure, and we will apply the David-Rick load. So the David-Rick load will start from 0 and it will increase to a value, then again from that value it will decrease. All right, so again it will decrease, that means so in the other cycle it will decrease, so it will come to 0. So we have this 0 again. In the other way it should go up, but that is not the case. All right, so it will remain 0 here. So from this is one loading condition, then we have the other loading condition. All right, so the sigma d which is applied by the loading ram can only deviate between 0 and sigma d. And we have the cell pressure sigma c. Now how can this be equated? All right, and this condition be similar to this condition which is developed in the in situ. So here we see that we have the initial pore water pressure and the initial confining pressure, that is 100 kPa and 200 kPa. So we can draw two more circles. All right, so initial confining pressure is 200 kPa here, and the initial pore water pressure is 100 kPa. So 200 minus 100 is equal to 100 kPa of effective stress. So we have this effective stress point here. Right. Now when we apply sigma d, now this is undrained condition. Okay, so volume change is not allowed. So no drainage from the sample. So undrained. No volume change. So only pore pressure will increase and decrease. Now when we start to apply David-Rick stress, so what will happen? This is the total stress condition here. So it starts from 200 kPa confining pressure, which is the cell pressure. So it starts from 200 kPa. And then we apply sigma d. Right? So from here, the Mohr circle will start to grow. Right? I'm drawing the half of the Mohr circle. Obviously, it will be the other way also. So the Mohr circle will start to grow as I apply the deviator stress. So ultimately from 0 we have applied up to sigma d. So we have applied up to sigma d. So this is sigma c here, which is 200 kPa, all right. And suppose we have applied sigma d around maybe okay, here 40 kPa it is given. Okay, so we have applied 40 kPa. So this is definitely 240 kPa, which is sigma 1. All right, so sigma 1 is sigma c plus sigma d, which is 240 kPa. Now what about the mean? So the mean stress, as the deviator stress will go on increasing, the mean stress will also go on increasing. So what will happen is that at this condition, so we have sigma c and sigma 1 240. So we have 240 plus 200 divided by 2, right? So that is equal to 240, 440 divided by 2, so we have 220. Now what is delta sigma? Alright, delta sigma is 220 minus 200, so equal to 220 minus 200 equal to 20 kPa, which is actually the center of the last Mohr circle here. Right, so this is the mean stress right here. So as the Mohr circle grows, the mean stress will move. So this is the center of the first circle, then there is the center of the second circle, there is the center of the third circle, then it will go on increasing and it will come up to this state. So mean stress will move from sigma cell pressure which was applied, so initially that was the mean stress. So from there it will grow, the Mohr circle will grow and the mean stress will increase to 220 kPa, which is the in delta sigma now is the the increment in the mean stress is now 20 kPa. Now if it is undrained case, obviously there is no drainage in the sample, and if we consider normally consolidated sand, right, so definitely delta U will be equal to delta sigma. And in fact this is not for only the last Mohr circle. All right, so when the Mohr circle will start growing, as we apply sigma deviator, we go on incrementing the sigma deviator from a zero value. So it started from the sigma cell pressure, so it first Mohr circle is this one, we have the center. So the radius of the Mohr circle is the increment in the mean confinement, and the same amount of Mohr circle, pore water pressure will be generated in the sample. So what will happen is that the effective stress Mohr circle will grow, but the mean effective confinement will remain same. All right, so here we see now if you consider now the present scenario, so we have a total cell pressure mean stress of total mean stress of 220. All right, so this is now the confining pressure of 220, that is the last stage, last Mohr circle. And similarly what will happen is that now increment is 20 kPa, so similarly the pore water pressure will also increase to up to 120 kPa. All right, so ultimately sigma c dash, all right, and or the effective confinement will be 220 minus 120 is equal to 100 kPa. So whatever initial effective confinement was there, the same amount of initial effective confinement is also after the loading has been completed. So what will happen is that the Mohr circle will shift the center of the Mohr's circle here, the confinement will remain constant because increment in the confining pressure is taken up by the increment in the pore water pressure. So what will happen? The Mohr circle will grow in this manner. Okay, so though the total stress is increasing from here to here in the towards the right side, due to the increase in the pore pressure, what is happening is that the mean confining stress is remaining at the same point. So what will happen is that, so here we have the start point. So we have 200 kPa. So this is 200 kPa and this is 100 kPa. So this is the effective Morse circle. So this is the effective Morse circle, effective stress Morse circle. All right, and this is the total stress Morse circle. Now as I start applying deviator stress from zero, we start from zero, all right, and the load is increased. So the load is given. So as soon as the load is given, what will happen? The Morse circle will grow. So now suppose we have a deviator stress of 10 kPa. All right, that is this deviator stress. So let us now sigma C was 200 kPa. All right, so it went up to 220 kPa. So this is 210 kPa. Sorry, so this is 210 kPa. To increase it, it increased to 10 kPa. So now what is the sigma 1 now? Sigma 1 is equal to 200 plus 10 is equal to 210 kPa. So that is sigma 1. So we have the cell pressure here. We have the cell pressure here, which is 200 kPa. Here we have 200 kPa. Here we have 200 kPa. So everywhere we already have 200 kPa. Plus we have the deviator load, which is 10 kPa. So we have sigma 1 now, 200 plus 10. All right. So the mean stress now is, mean total stress is now 210 plus 200 divided by 2, which is equal to 410 divided by 2, it is 205. So what is delta sigma mean? It is 200 and delta sigma mean is 205 minus 200. Right? So that is the increment in the mean stress, mean confining stress. So that is 5 kPa. Now since it is undrained, so there is no volume change. All right, no change in pore water. So there will be increase in the pore water pressure. All right, so the initial pore water pressure was 100 kPa. So as soon as the mean increment we observe, that is 5 kPa, same amount of pore water pressure will also increase. So it will be increased by 5 kPa. So now the pore pressure is 105 kPa. So since now the pore pressure is 105 kPa and the mean total mean stress is, confining pressure is 205 kPa, what is the effective confining pressure? So effective confinement is again sigma C dash is equal to 205 minus 105 is equal to 100. So thing is that due to the development of pore pressure of 5 kPa, so this here more mean confinement will remain, effective mean confinement will remain at the same point, though the increment is actually occurring, the total increment of the total stresses is occurring in the towards the left, towards the right, sorry, towards the right direction, right? So in the, as the deviator stress will go on increasing, we will have the increment of the Morse circle in this direction. All right, but you can see the effective mean will remain at the same point and only the Morse circle will go on increasing, the diameter of the Morse circle will go on increasing. And then again, as we release the, now we have applied up to the maximum sigma deviator, right? So this is the maximum sigma deviator, then we start releasing. So as we start releasing, again the diameter of the Mohr circle will start to shrink, and it will again come back to the same point. So this is 100 kPa, and this is again 200 kPa. Now one thing you have to remember is that here in this conditions that we have discussed, we have considered the load to be applied very slowly. All right, the deviator load, deviatoric stress is applied very slowly. So thing is that while doing a triaxial test by applying a cell pressure of sigma c and applying a deviator load of up to sigma d, cycling from 0 to a maximum load, and then again up to 0, again up to a maximum load, again up to 0, again up to maximum load, so we can replicate the same condition which is occurring in the field. All right, so in the field we have the mean constant, and the shear stresses is going on increasing and decreasing, going on increasing and decreasing. All right, so the initial stress condition is preserved, so that condition is also here replicated. So we have the initial total stress 200 kPa, 200 kPa, and pore water pressure 100 kPa. So we have the effective confinement at 100 kPa. Now as we go on increasing the total pressure, the deviatory load, we go on applying the deviator load, the Mohr circle will develop, total stress Mohr circle, the total stress Mohr circle will develop towards the right. So here you see it will increase towards the right. All right, but with the development of pore water pressure, what will happen is that the effective confinement will stabilize at that same point. All right, so here we have the same point, whereas the Mohr circle here is developing on the right side. All right, so sigma d is increasing, and therefore sigma c is remaining constant. So this is sigma c, right? It is remaining constant at 200 kPa, and we have increasing the sigma d. All right, so with increase in the sigma d, so this is the increase in the mean effective confinement. So it is equal to the radius. So what happens? The same amount of pore water pressure will also generate. So it will stabilize the effective confinement at that same point. Right? So it is not moving with the, it is not going on towards the right as in case of the total stress. So the effective stress here, only the shear stress is increasing and decreasing and again reversing the direction, and the same condition as in situ field is replicated. Now this cycle is only for a very slowly applied load, all right, so that there is no condition of dynamic loading or oscillation or vibration being developed in the soil sample. All right, so it is very slowly applied, so that only pore pressure is generated, and it is equilibrated at the same time as the load is applied. So the increment in load is same as the pore pressure is also equilibrating within the soil sample. So it is very slow, right? Just to see whether the effective confinement in the sample is as it is replicated in the field condition or not. So here now here we can say that constant mean, so the constant mean and extreme principal stress, all right, so it is satisfied as in the in situ condition. Now thing is that we will apply dynamic load. So now you can see here within 1 second already two increments of load are already applied. All right, so this test which was done by Seed and Lee in 1966, the frequency of dynamic loading or the dynamic vibrator stress, deviatoric stress which was applied, so it was 2 hertz. All right. So now initial pore pressure was 100 kPa. Initial pore pressure was 100 kPa, and as the loading was applied, then it reduced to 0, again applied, again reduced to 0, again applied. What happened? So with consecutive cycles, pore pressure got developed. Now what will happen if the pore pressure will develop? So definitely with each cycle, this Mohr circle will grow and shrink, again shrink. All right, and then again it will go to the other side, again it will shrink. All right, but now there is development of pore water pressure, excess pore water pressure, apart from what was developing in the previous case. So here sigma d by 2 amount of pore pressure was developed. All right, for each increment, slow increment of, so here this is, if you consider here, this is sigma 1 is equal to sigma c plus d. So this diameter is sigma d, this diameter is sigma d. So increment in the pore pressure or total stress is sigma d by 2. Right, so that is the increment in each step. So we have sigma d by 2. All right, so here we have some values of sigma d. So this is the diameter, so that is a sigma d. So we have sigma d by 2 increment in total mean confining pressure, and similarly that same amount of pore pressure was developed. All right, so since that same amount of pore pressure was developed, what happened is the effective mean confinement, it remained in the same position, it did not change its position. But with application of dynamic loading, here we see, so very quickly the load is applied, there is now increment of pore pressure beyond this value. All right, beyond this value, and the pore pressure is going on increasing with each cycle of loading. So what will happen is now, so here the effective stress condition was here initial, so this is initial. Right, first cycle means first cycle I can say. So first cycle I can say it increased to this value. So it started from this point, so that is the first point, initial condition. So this is the initial condition. All right, and this is the initial condition of the total confining pressure. All right, and then we applied the deviatoric load, so this Mohr circle developed in this manner. All right, and it got developed in this way, while sigma d by 2 pore pressure was developed. So the mean effective mean confinement remained at the same point, and only the shear stresses developed in the sample, or the deviatoric stresses developed in the sample. Now with each cycle, so this increment coming to same point, again going down, or let's change in direction, that is, so that increment is 1 cycle. So with increase in cycle, so we can see with increment of cycle, what will happen is that the more effective stress Mohr circle, it will now start sliding towards the left. We know sigma dash is equal to sigma minus u. So with increase in pore pressure, total stress condition remaining same. All right, so it will vibrate. So 200 kPa we have already applied here, 200 kPa it is remaining constant, and this will vibrate between 40 kPa and 0, 40 kPa and 0. All right, so total stress will grow and shrink at the same point, but with increase in pore pressure, this Mohr circle, the growing and shrinking will be there. All right, but the total entity will start moving towards the left. Now at this condition, it has reached the failure surface. So this is the initiation of the liquefaction. All right. So here what will happen is that, so here you see, so this is the initial condition. All right. So this is the first cycle. So after 20, 10-20 cycle, it may still remain here. It will go on increasing, decreasing, go on increasing, decreasing. All right, and it will start moving. All right, so there will be development of pore water pressure, and it will start moving in this direction. And then suddenly, when it starts to reach the failure condition, so here you see, so there is no axial deformation for the initial cycles. All right, as soon as it reached here, so we have now the axial deformation started. So as it goes on, all right, so we have total liquefaction. All right, so the load also required to actually keep on deforming also reduces, but here, since it is stress control test, so the load is remaining constant, the deformation is going on increasing. All right, and ultimately we will have a total liquefaction where sigma dash is equal to sigma minus u is equal to 0. All right, so it is here at this point. So effective confinement is 0. But the total confinement and the total deviatrix, the Morse cycle total stress condition will remain same here, right? Because that is what is applied. That is what is applied. Right? We are still applying 200 kPa of confinement, 200 kPa of confinement. But thing is that now the pore pressure here is also 200 kPa. So effective confinement is 0. Right, so here it was around, this is 200 kPa, the pore pressure was around 170 maybe. Right, so a small amount, 30 kPa of mean effective confinement was there. So here it is there. Right, so up till this point, maybe this pore pressure is around 150 kPa. All right, so up to this point the soil was, it was not deforming as such. All right, as soon as it reached the failure condition, there was, significant amount of axial deformation observed in the sample, and the sample can be said to have started to liquefy, and there is, quick increase in the pore pressure. So here you see, so from here there is very sudden increase in pore pressure, all right, and the effective confinement suddenly becomes almost negligible. So that is how the soil liquefies. All right, so this is the liquefaction simulation in the laboratory. All right, using the triaxial test. So this is cyclic triaxial test. Right, so ultimately here we see that whatever stress condition, that constant mean and extreme principal stress condition was ultimately maintained in this manner. All right, so thing is that if so whatever increase in the total cell confinement happened, and same amount of increment happened in the pore water pressure, and therefore that aided in stabilizing the effective confinement at the same point. So the Mohr circle, it only grew in radius, so extreme principal stress, all right, mean, constant mean, so constant mean, extreme principal stresses, right, then again it will shrink back. So the pore pressure aided in taking that into consideration. So this is a test done by Seed and Lee in 1966. So extensive tests they have done. All right, so you can see with increment in load, with increment in deviatoric load, so cycles they have applied, All right, so we can see there is an increase in the pore pressure, and when it becomes 200, so there is total liquefaction occurring, and only after certain numbers of cycle we can see that there is significant amount of strains being developed in the sample. All right, so initial void ratio was 0.87 of the sample, so the relative density was 38%, so the sample can be considered to be a loose sand. Right? It can be considered to be a loose sand. So here we see the axial strain only developing after certain numbers of cycles. All right? And ultimately the effective confinement was nullified by the pore water pressure. All right? So, and then significant amount of strains occurred at that moment. And thing is that here, as I've shown here, so suddenly what they did is that sigma d by 2, the initial excess pore water pressure, right? The initial excess pore water pressure, what they did is they corrected the same from the pore pressure measurement during the cyclic triaxial application, or cyclic Davitrov stress application. Davitric stress application. All right. So whatever pore pressure developed was measured during that condition, that was corrected here. So this is the measured pore pressure. All right. So this is the measured pore pressure, and this is the corrected pore pressure. So they did the correction. So as I have explained in the previous case, so only thing is that that increment in the pore pressure actually is helping us to keep the stress condition equivalent to the in situ condition, right? So that is actually one advantage. So here you see with increment in pore pressure, ultimately we have liquefaction, right? So it will move like this, total stress remaining same. So similarly there is cyclic simple shear. Unlike direct shear, so in direct shear what we are doing is we have the sample and we apply movement to the sample at the bottom. The sample is moved and a reaction is actually applied here. All right, and a reaction, tangential reaction is applied here. So we have the proving ring, all right, or the load cell, and whatever load is required, whatever stress is required or force is required to shear the sample, all right, shear the sample, that is measured by this load cell. So that is why direct shear. So we are directly shearing at this plane here, right? So this is the normal stress measurement. So this is the normal stress which we are applying, and this is if the soil expands in volume or contracts in volume. All right, so that is the measurement we can do, and this is the horizontal stress strain. All right, horizontal displacement measurement. So how much it has moved in this direction, and this is the reaction from the sample. It is measured by this load transducer or load cell, or you may have also a proving ring. So that is direct shear. Now unlike direct shear, in the simple shear what we have is, so in direct shear these are stiff sides here. Alright, these are stiff sides and the sample is directly sheared through this plane. In the simple shear what happens, we have a flexible kind of encasement here. So the sample is sheared in this manner. All right, so that is why it is called simple shear. So only shearing is occurring. Only shearing is occurring. All right, so only shearing is occurring. So it is swayed in one first in this direction, then in the other direction, then again in this direction. All right, so that is how the cyclic shear stress is applied in the cyclic simple shear. Right? So you can see this is the shear stress. So it goes first in this direction. All right, so it goes in this direction, then it goes in the other direction, so it goes in the other direction, then again it goes in the same previous direction. So there is a change in direction with loading cycle. All right, so that is the cyclic simple shear. Now again, as in case of cyclic triaxial, so what we observe here is increment in pore water pressure. All right, increment in pore water pressure. Then suddenly here we see that at a particular point, as in case of triaxial here, up to a power point there was no deformation in case of simple shear as well. All right, so up to a number of cycle, some numbers of cycle, there was no deformation. So this is 24 cycles is total 24 cycle. That means the sample, I mean liquefied, the sample liquefied after 24 numbers of cycle. So this is Monterey's sand. It was done by Seed and Peacock. Right, it was done by Seed and Peacock. Okay, so here you see that up to a certain point there was no deformation. Then suddenly again, so as I have explained that the Moore circle, the effective Moore circle moves towards the left. That means the effective confinement, mean effective confinement is reducing. So the mean effective confinement is reducing, and ultimately it touches the failure surface. So as soon as it touches the failure surface, extensive amount of shear straining occurs. All right, so that is the same case is observed here as well. So after doing so many tests, after doing so much of tests, so various researchers over the time, they developed certain relations. All right, so we have, I mean, the first criteria. So the first criteria, as was given by Arthur Casagrande in 1936. So we have the critical void ratio criteria. So he said that if the soil is on this side of the critical void ratio line, so the soil is susceptible to liquefaction. If it is below this, all right, it is non-susceptible. But as we have seen here, this is below, this is the critical void ratio line, this is below, but it liquefied, and this did not liquefy. All right. So Castro 1969, Castro was a student of Casagrande, and he did his research under Casagrande, and in 1969 he proposed the steady state of deformation as a criteria for defining liquefaction of soils. All right, I mean, he proposed the idea of the steady state of line for defining the liquefaction criteria. So Casagrande in 1976, he said that when there is liquefaction, actually there is a flow structure being developed in the soil. So the sand grains, what happens is that they continuously roll or rotate to orient themselves in the structure of minimum frictional resistance. So when we do triaxial test, when he did triaxial test to obtain the critical void ratio line, this particular factor was not taken into consideration. So Castro, he did series of tests, all right, and I mean the tests were developed to take this into account, and after the test results were plotted, he came up with the idea of steady state of deformation or steady state line. All right, so what is the steady state line? So he did a series of tests. So this is the initial state of stress condition. So we have effective confinement P dash. All right, so this is P dash. and we have an initial state of steady state. This is called the initial static stresses, all right, static shear stresses, Q. Right, so that is already in the soil, that is in, it is present there, all right. And then he did a series of tests. So sample A is a very loose sand. So sample A is a very loose sand. Sample B is a very dense sand. And sample C, it actually lies very close to the critical void ratio line, right? But it is below the critical void ratio line. That means it is on the denser side, right? So if we consider this here, so maybe somewhere here, right, or here, so in this state. So that is C, right, intermediate density. So A is very loose, B is very dense, and C is very, I mean, it is in the range of just, I mean, denser to the critical void ratio line. So what he did, he sheared the samples, all right, he applied dynamic loading, and here he observed that at a particular confining stress, all right, if we start from the confining stress here, so there is development of pore water pressure, and the soil A, it traced this path, all right, and now there is constant deformation here occurring. So this is the line of failure. So this is the line of failure, or we can say the steady state of deformation here. All right, so he observed that there is a constant deformation at this point A. All right, so this amount of deviatory stress is there, and this amount of confinement is there, and this particular point, this particular loose sand, it moved from this point through the development of pore water pressure, and uh, I mean, when there was increase in pore water pressure, there was decrease in the effective stress, right? Decrease in the effective stress, and therefore the soil, it started to deform, and ultimately there was a constant deformation at this point. Similarly, so here you see this is the point A. So we have the pore pressure, I mean, when it reached the point A, the pore pressure remained constant over the deformation, further deformation, that is. Right, so that is the steady state. In case of the C, point C, all right, so initially there was increase in the pore water pressure, and then after shearing, what happened is it expanded. All right, after shearing, it expanded. So initially there was some liquefaction. All right, so this is the limited liquefaction. So this limited liquefaction which is occurring here. So here limited liquefaction occurred, but then after the soil was sheared, the state of the soil got stabilized. All right, so that is the limited liquefaction case. Whereas B, now B is a very dense sand. So when the B was sheared, so instead of pore pressure increasing, the pore pressure decreased and the effective confinement increased, and therefore it moved a wave up. All right, so the effective confinement increased, and definitely the shear deviatoric stress required to cause deformation in the sample also increased. All right, so this is the B soil sample type, and this is the A sample type. So this is the range of liquefaction here. All right, and then we have the limited liquefaction of the sample C. So he did So what he did is he obtained these points over a range of series of tests for different confinement and different uh, deviatoric load and different void ratio, and he developed the steady state line. Alright, so this is the steady state line. Now the steady state line had three parameters governing, alright, governing the steady state line. So we have the void ratio. So this is the void ratio axis, alright. Then we have the effective confinement axis, right? Effective confining axis, effective confinement, and then we have the shear stress, right? And then this is the failure line, shear stress versus effective confinement. All right, so this is the failure line, and this is a projection of E and confining stress on here. So this is the steady state projection of the steady state line for the E versus confinement axis. All right, and similarly we have the E versus shear stress plot. All right, so all of these three parameters, it was combined into a single line in 3 dimension. Right, we have the steady state line. Now if we separate it out, we have shear stress. So if we plot shear stress versus the E, all right, so this is the log. So if it is not log, if it is linear, so then we will have this kind of plot, right? Since it is semi-log, right, so the shear stresses were plotted in log, so we have a straight line. All right, so from this particular criteria, Castro 1969, he proposed that if the state of the soil, if the state of the soil is above this line, then the soil is susceptible to flow liquefaction. All right, and if it is below, it is not susceptible to flow liquefaction. All right, and this line, it falls slightly below the critical void ratio line. All right, so how did he arrive at that? So we have here, what we have is a point, a sample at the point A. So it is at a particular effective confinement. All right, it is at a particular effective confinement, and it has a particular void ratio. And obviously, seeing the plot of E versus this effective confinement, you can see it moves straight to the left. It moves straight to the left. So first of all, we can infer that it is undrained. Now what happened is that the soil is sheared. So for some small amount of stress, it will there will be not much significant amount of development of pore water pressure. All right, and there will be a very small amount of deformation as well. So what will happen is that from point A, when we plot it in P dash and Q, so P dash is equal to P minus U, and P is equal to sigma 1 in case of triaxial, or in case of this three-dimensional case, it is sigma 2 plus sigma 3 by 3. All right, so in case of triaxial test, it is sigma 1 plus twice of sigma 3 by 2, and Q is sigma 1 minus sigma 3, which is sigma d. So here he has plotted by sigma d by 2. That means the deviatoric load